as Barbara said, this is the first talk in seismology. My name's Steve Grant. I'm from the University of Texas. I won't go through all of this, but there's a lot of other topics coming on. I'm going to give you the introductory equations, kind of the real basics of seismology. Some of the later talks will get into the exciting things like tomography and whatnot, but I won't touch on that. So my outline here is a brief introduction, simple introduction to what are seismic waves, what is seismology. Then we'll talk about the fundamental equations, so kind of like Mike was doing with geodynamics or convection. After that, I want to talk about the behavior of seismic waves in different situations. So we'll talk about waves in layered media. We'll talk about ray theory and the basic structure of the Earth. And if there's time, I brought some examples of different what's called body wave studies that I thought were kind of interesting and relevant to the group. So what are seismic waves? Well, they're vibrations or deformations inside the solid Earth that propagate, that travel through the Earth. And everybody's familiar with water waves. So just put a picture up here. You throw a pebble there, you get a water wave expanding out. You all realize this crest in the water propagates out. If you look at an individual molecule of water, though, the individual molecules are just going in little circles like that. They don't actually travel with the wave. So I show this because you're all familiar with water waves, but there's two different velocities involved. One is the velocity of that crest. We call that the wave velocity. The other velocity in seismology, we call it the particle velocity, but it's the velocity of one particular piece of material. Notice for the water waves, little atoms or molecules of water are going around like this. As you go deeper and deeper in the water, the molecules move less and less amount. And in seismology, like I said, we have similar kinds of waves, but they're within the solid Earth. And we have two words, body waves and surface waves. So my talk is supposed to be on body waves as opposed to surface waves. Jean-Paul Montier will talk to you about surface waves. The water waves are a good example of surface waves. So the water wave or surface waves in an elastic Earth shake the surface. They also shake deeper down, but they get smaller and smaller shaking, basically an exponential decrease. We call those things surface waves. Body waves, on the other hand, expand in 3 dimensions. So if everything's kind of homogeneous and you had, say, an explosion at a point here, you will get a disturbance in a sphere around that point, and it will propagate outwards in all 3 directions. And we call these kinds of waves body waves. So that's kind of what we're going to be focusing on here. Really, the two things obey the same equations and could be done seamlessly going between the two, but we'll focus on those body waves. I do mention something about the decay in amplitude. Maybe this is premature putting it up there, but I did. So the surface wave, if you think about it, it's stuck on the surface. So as it expands out, the circumference of the circle is increasing as r, distance from the source. The body wave, however, is propagating in 3 dimensions, and the area of the sphere is proportional to r squared. So to conserve energy, and it turns out the amplitude of the shaking squared is proportional to energy, the surface waves decay is 1 over the square root of the distance they travel. The body waves decay is 1 over the distance that they travel. And that's why in a lot of seismic recordings, the surface waves are quite large. So let's go on from there. I thought I'd show you an example of a fairly simple seismogram. This is the movement of the ground in the east-west direction at a station recorded in La Paz, Bolivia. And this movement was recorded a short time after a deep earthquake just south of La Paz in South America occurred. So if you look at the recording, very simple, right? It's just how the ground moves in the east-west direction. You see a number of these pulses, boom, 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 coming in time. We call those things phases. They're basically waves, these elastic vibrations that are arriving at the station in La Paz. If you look at a blow-up, let's say just this big pulse here, and I just blew up 100 seconds, or actually my student did, of that pulse, you see that, the ground was pretty stable. The ground started to move west, moved east a little bit, moved back west again, came back to its equilibrium point, and was flat afterwards with a little bit of jiggling. We call this thing the wave shape, or the pulse shape, or the wave form of the particular wave. So I'll kind of refer to that a couple of times later on in the talk. But that's basically what this pulse looks like when you blow it up. So what are all these different pulses? And it turns out in this case it's kind of neat. La Paz was very close to where that earthquake occurred. And what you're seeing with those pulses are waves that went down to the core and up to the surface, also to the surface, and et cetera. So the very first pulse went from that earthquake source directly to the station. The second pulse you saw went down to the core, bounced off, recorded at the station. The third pulse up to the surface, down to the core, back up, et cetera, et cetera. And that's what those different pulses are. A lot of seismology is basically about speeds, and you've already heard in a lot of talks wave speeds here and there, ultra low velocity zone, et cetera. This is a nice little experiment you could do just looking at that recording. If you know how deep the core is, 2,891 kilometers, you could just look at the pulse that went up here, and the other one that went up, down, up. Measure the time difference between the two of them, and you can get the average speed of the wave going through the mantle. So it turns out to be about 6.2 kilometers per second. Very simple calculation. But really, a lot of seismology is basically in that way, getting the speed of these waves. This is wave speed, not particle speed. So I want to mention something kind of basic, but I think it's really critical in seismology. And I think all of you have had Fourier series. So you can take any function, and let's take this red one, that's just a pulse, a Gaussian type pulse. You can make it, you learned in college, I guess, undergrad, by summing together a lot of different cosines and sines. So in this particular case, because of the symmetry, these are different cosines with different wavelengths. You add them all up together, you get that black line. If we added more and more, you can reproduce any shape function by adding together these cosines. Fourier series, that's kind of well known, I think. But maybe a little bit less well known is you can actually represent a wave, so a pulse, like that pulse shape I showed you at La Paz, that particular shape, propagating through space. We can also represent that by cosines and sines as well. It's cosines and sines of two coordinates now, the x, the distance, and time. So we can add up a whole bunch of these cosine kx minus or plus minus ft's together, and we can make any kind of propagating pulse. This is a nice little video of how a function like that actually represents a wave traveling. And I'm not sure these are going to... Oh, there it goes. This was made by Ved. And basically, an individual particle is just going up and down like this. But and this is distance x over here, and you're just computing these things as time goes on. So I won't show the video again, but you see the peaks traveling along. So that's the wave propagation part. So we can make any kind of seismic wave out of these cosines. There's a lot of terminology here. The time it takes to go up and down like this at one particular point is called the period for the particular wave. That's 1 over the frequency. The frequency's up there in the cosine expression. Wavelength is the distance between two of these peaks here, or 0 to 0. The velocity of the wave, how the peak travels, is just the wavelength times the frequency. There's a whole bunch of different combinations, wavelength divided by the period, etc. So often we take seismic data like the seismogram I showed you, and people will filter it. They will make that seismogram out of a bunch of cosines with different frequencies, different wavelengths. They'll only keep a few of the frequencies and wavelengths in a particular analysis that they're doing. And why I think that's important is whatever you're trying to get out about the interior of the Earth, whatever resolution you're looking at, you are limited to about a wavelength. That's the absolutely best resolution you can get. So whenever you read a paper from seismology, you should look at the period range they're looking at, what are the wavelengths, and you know that's kind of the limit of the resolution. You can get an average property in a wavelength. You just have no idea what the details are within that particular wavelength. So I filtered that original seismogram here, those pulses at La Paz. I didn't mention it before. This was from 1 second to 100 second period, all those cosine waves. And that's pretty much what the ground did. The amplitude at higher frequency than 1 second, very, very small. Longer than 100 second, very small. Pretty much that's what the ground did. If you filter that record 50 to 100 seconds, you get this result. It's a beautiful seismogram, but it looks quite a bit different than that. A lot of the global tomography, we tend to use longer period, not quite as long as that. And here's kind of interesting, this is 1 to 10 seconds, so the shorter periods in that particular seismogram. And there you can see that first pulse here, you can see maybe the second one there. You really don't see these later pulses. The high frequencies have disappeared. You see a lot of other stuff going on. I have no clue what that is, but it's something. So I wanted to make, well, that's the young seismologists will figure all that out. Wanted to make the point about frequency content in seismology because it's very important. We use a huge range of frequencies, over 5 orders of magnitude. The oil companies, reflection seismology, they're looking at 100 hertz waves. Body waves in the deep earth, usually from about 1 second period, maybe 20, 30 second period. Surface waves from about 10, maybe 5 second period, up to a few 100-second period. Normal modes, Miyake will talk about them, up to 1,000-second period. So there's a huge range of these different periods, different resolving capabilities, different usefulness in these different waves.
Could you explain a little bit more, how do you do the filtering exactly? Do you have to Fourier transform it first into the frequency space and then filter there and then transform it backwards?
Yeah. So that's exactly it. You can take a time series. You can do a Fourier transform, get the Fourier components. Usually don't cut off at a particular frequency. You kind of put a window on it and smoothly get rid of them. And then go back to the time domain. And that's basically what was done there. Yeah, just interrupt if you have any question. So that's kind of my intro on the seismic waves. So we'll go through some basic equations governing the waves. They're the same equations for surface waves, normal modes, and body waves. So we'll just do it once, I think, here. I'm not going to show you a whole lot of equations. I think you can look them up. But maybe the usefulness of this is just to see where certain things come from, what approximations were used here, what approximations there, etc. So let's start with that. And seismology is about movements or deformations that propagate. So how do we quantify movement? And we introduce what's called the displacement vector. And a lot of things, I'm going to be repeating what Michael talked about yesterday, but he was using velocities. And I'm glad you didn't use U, you used V. So we're using
mechanics people use U for velocity.
Yeah. So we're going to repeat a lot of things, but they're different. And I'll try to make that clear. Anyway, we introduced a vector. It's a vector field. Every point in space, so let's say x naught is really x, y, z in space, the vector at that point is just the displacement of that particle who at equilibrium is at x0, how it's been moved from its equilibrium position. So the coordinates kind of refer to particular particles. The vector associated with that coordinate is how that particle has moved. So it's a vector, it has 3 components, right? Up, down, north, south, east, west, whatever system you want. Seismic waves are deformations, and you know the displacement vector of all the particles everywhere. Well, maybe you know the deformation. You do in a sense, but it's not directly the displacement. You can imagine if I said the displacement vector everywhere is 1 in the x direction, 0 in the other directions, it just means the whole body shifted a distance of 1, right? No deformation has occurred. So deformation has to do with changes in the displacement vector as you go from point to point. And I should just mention quickly, I'm spending a little bit of time on this displacement vector. Most of the equations in seismology are equations for that thing, so it's important to know what it is. So this, again, came from Weg, a nice little illustration of deformation and how it's related to the displacement vector. He shows different situations. So imagine, so we have the x1 coordinate going to the right, x2 going up and down. Let's say the displacement vector only has a component in the one direction, but that the displacement vector is increasing as you go in the x1 direction. And it is constant as you go in the x2 direction. So what happens, what he had here is a pink little block. After some deformation, all these particles that were on the left there have moved a little bit to the right. all the particles that are over here, they've moved a lot more to the right. So that original square that was here before has now become stretched, basically. So it's changed shape. In this particular kind of deformation we call a normal strain deformation. I'll come back to that a little bit more. But notice that it's related to, you can imagine, the derivative of this displacement vector component in the one direction with respect to the one axis. Now, you can look at a different situation where, again, we have displacement only in the one direction, no other component of displacement, but that displacement is varying as you go in the x2 direction. So again, that has made this thing, little bits of displacement here as you move along in the x1 direction, okay? Excuse me, as you go up in the x2 direction, you have larger displacements up here than you do down there. And what has basically changed is you had an original right-angled block like this. You can now see that block has changed. I can't really see what I'm looking at here. Yeah, you can see this angle here used to be a right angle, but now it has changed shape. It has a more larger than 90-degree angle. The idea of changing an original right angle in the material to a difference in that angle between two perpendicular faces, if you want, we call shear strain. And you can see that it's related, hopefully, to a change in the displacement vector in one direction as you change your coordinate in a different direction. I'm sorry, yeah?
Well, I think there's a shear strain in the left one also,
No, I don't think so.
because the shape changes.
There should be.
There
it's
is
just
if you-
screwed up.
That's screwed up?
No, I actually didn't screw it up. if you draw a rhombus inside the square, you will see that in the leftmost case, when you stretch it, the internal angles of that rhombus will change, and therefore there is shear there.
The angles are changing in this thing?
Yes,
Even with
because you just have to look at the angles that are like 45 degrees.
Oh, not in the x, y.
Not those
Z
angles, but the
coordinate
other.
system. Yeah, so
Yeah.
within here there's some shear, but not in these coordinates. Yeah. So, anyway. This is going to go great if I'm already stuck. So we're changing angles, and there is some shear within here at different angles. And it's related to the change in the displacement vector as you change a coordinate. However, you can change displacement vector as you change a coordinate in a way that does not really change the shape of the material. And here is where you're changing the U1 displacement here as you go in the x2 direction, but you're changing the u2 direction or displacement as you go in the x1 direction. And to first order, if these two things are equal, then you just have a rotation of the material. Okay? So it's not directly just derivatives of these things giving you deformation. You have rotation due to gradients in the displacement vector, as well as stretching, as well as angular changes in original right angles. So we write the strain tensor, or strain matrix if you want, EIJ, and that has to do with the components changing the angles of right angles, as well as the stretching and contraction along certain axes. So using the X, Y, Z axes, this matrix here is the rotation aspect. If you add the two of them together, you'll just see the derivatives, each combination of derivative displacement versus axis combined. But this is the part we call the strain tensor. So it's a matrix if you want. This is the 2-2 thing. That would be E22. And you can see the connection between the strain and the displacement vector. And very important, I should mention, this is just an approximation. So if you define the normal strain as delta L over L for a particular line element, say along the x-axis, that's approximately di-ux di-x, but it's not exactly di-ux di-x. You have to use what's called finite strain theory to relate the displacements to strain in that way. These equations are what is called infinitesimal strain theory. Very, very small strains. Generally in seismology, the seismic waves we look at have strains 10 to the minus 5 or smaller. So we always in seismology use this particular theory, infinitesimal strain theory, to relate change in shape or strain to this displacement vector. Okay? The other thing I'll point out is the elements on either side of the matrix are identical by definition. There's no physics there. They are the same thing if you just look at the equations. So the matrix is symmetric. The other thing I might mention is displacement vector is a length, dividing by a length. So this is unitless. Strain has no units here. Okay? So we talked very briefly about change in shape, relating that to this displacement vector. Seismology is all about forces causing the deformations that end up propagating. So we have to talk a little bit about forces, and this is something Michael did talk about. He used T for stress, and I'm using sigma, so apologies there. And keep you on your toes, I suppose. So what we do, if you have a continuum, a solid material, you take a tiny little element inside that solid material, and what we'd like to do is know all the forces on that element, and then to get the equation used in seismology, we'll equate those forces to the mass times the acceleration. So what kind of forces can exist in general? I don't know where they came from. In general, you can have what's called body forces, and they are proportional to the volume of this little element. Gravity is an example, body force, electric forces. Everything you learn in high school and beginning undergrad is body forces, basically, proportional to the volume of the material. But inside this large body, if you want, this little element is existing there, you can have what are called surface forces, or I like to call them sometimes contact forces, literally the forces of a sheet of atoms right next to that plane there of atoms, putting forces on the plane that exists within this little body here. So we call contact forces or surface forces or stress. And they're a little more complicated. The body force, 3 numbers, right? It's a vector, force X, Y, Z. Surface forces got all these different faces. So there's 6 faces in this little cube. On each face, presumably, you can have a vector, so 3 different numbers describing the force on the face. So altogether, 18 different numbers if you want to know the surface forces acting on this little element. So it turns out it's not quite that bad. If we shrink the element down to a point, the stress or the traction or the surface force, all the words are equivalent, they're the same on opposite faces if our element is at a point. Okay, in the limit of it being a point. And there's one other thing that's the same, and Michael mentioned this before. If this element is really a point, its volume is going to 0, the surfaces go to 0 less quickly. Therefore, at a point, you can't have a torque on the element, which means, and Michael went through this before, that the surface forces, for example, 2, 3 here, have to be balanced by the surface force 3, 2. There can be no torque on a point element. So and I didn't even define what all these things are. These are all the different surface forces acting on this little element. The nomenclature, the first number here, represents the direction of the force. The second number represents the normal to the plane that the force is acting on. So sigma 3, 2, force in the 3 direction on a plane perpendicular to the 2 direction. And that's the opposite of here, because this diagram has the opposite convention. But sigma 3, 2 is always equal to sigma 2, 3. Always, always, always. So you can reverse the convention, and people do. Actually, people have different conventions for that. So I guess I should have said force is the second number, but I prefer it to be the first. 2 direction, this is the face perpendicular to the 3 direction. So always symmetric. We're talking about a point. Opposite sides have the same thing. That gives you 6 independent numbers to describe the surface forces acting on a material. The units for these guys are force per unit area, or pascals, and okay, well, we'll have to use talk about that. An important point that I think is kind of subtle is if you talk about deformation of a material, it is due to these surface forces, stress. is really independent of the body force. The body force, the gravity, does not directly deform the material. Okay? It's the stresses that deform material. And therefore, you can do something, writing equations, relating stress to strain, deformation. You can do that and not worry about the body forces. So that's true geodynamics, seismology, whatever. So Michael talked about constitutive laws, and that's just a relationship between those stresses, those surface forces, and the strains. And there's a lot of different constitutive laws, and he gave you one, Newtonian viscous material. In seismology, we use a constitutive law called linear elastic behavior. Linear elastic just means that the stress is linearly proportional to the strain. It's instantaneous, and that means that if I put a stress on a point, the strain immediately happens at that point, and it's reversible. So you relieve it, you put a stress, you deform the material, you relieve the stress, boom, it bounces back to the way it was originally. So why do we use that? Well, that's a pretty good approximation to the behavior of almost all materials, as long as you're looking at short times and small stresses or strains. And that's kind of seismology, right? You're looking at something that happened over a 10-second period or time. Very, very small strains, 10 to the minus 4. So always in seismology, or almost always, 99.9% of the time, we assume linear elastic behavior and an equation to say just what those words say there is that any stress, sigma ij, where I can be 1, 2, 3, j 1, 2, 3, is equal to some constants times strain, E 1, 2, 1, 1, 1, 2, 1, 3, etc. So Michael actually put this up. These constants, I think, are different than the constants you put up, because they're for this linear elastic behavior. What are they? We call these constants. They're a property of the particular material that you're looking at, the elastic constants. They are relating, remember, strain has no units. Stress is force per unit area, so these elastic constants have force per unit area. What they are basically resistance to deformation, right? A stiffness of the material. A higher value of C will give you a lower value of strain for a particular value of stress. As Michael mentioned, there's 81 different C's in this equation. You can change I1 to 3, J1 to 3, K1 to 3, L1 to 3, etc. 81 of these C's, 9 different strains, 9 different stresses. We already said that E12 is the same thing as E21 by definition. And therefore Cij12 better be the same as Cij21 because they're multiplying the same thing basically. So there's a lot of symmetries in these 81 different C's. And in fact, it turns out that in the worst case scenario, the least amount of symmetry possible, you have 21 independent values for these elastic constants. So that's related to the crystal structure of the rock or the mineral that you're looking at, what those C's are, as well as the temperature, etc. So that's kind of important when you talk about anisotropy later on. You're dealing with all these different C's. Why 21? I don't have a good intuition of why exactly 21, but why is it more than just a couple? Well, basically you're saying if I squish material this way, I get a different shortening than if I squish it that way or I squish it that way, right? You can imagine because of the crystal structure, you get different behavior for squishing in different directions. One final thing to note here is some of the later equations are going to do that. Here the summation is explicit, so you're changing L and K, 1 to 3, summing them all together. We use something called the summation convention. It makes the equations a lot easier to write down. That if you write an equation with indices like this, and you have two indices which are the same in the equation, it implicitly assumes you're summing them together. So this is identical to that. You're just dropping the summation terms there. So,
Stephen,
yeah.
so there are 21 independent values, and presumably that's for a triclinic crystal, and obviously for an isometric crystal, then there's 2.
Actually,
you're going to show that.
3. It's an interesting point. It's for a liquid. There are two independent constants
Okay.
for an amorphous material, but for a crystalline material
Crystal
with cubic
isometric class,
symmetry,
there's three.
there are three independent elastic
Okay.
constants, so they can be anisotropic, actually, elastically.
And then when you go to different crystals, so say you had an orthorhombic crystal, there wouldn't be 21, there'd be less.
Right.
You just put the symmetry of the crystal in and...
Absolutely. So people have done this. Actually, the place where I saw all the symmetries done to go from 21 to 2 is Feynman lectures. He actually has a
Oh,
chapter
okay, yeah.
and he goes through all of that.
Cool.
I'm really ashamed. I have not done that. So orthorhombic and cubic and hexagonal.
Right, go
And
through
I don't
the-
know how many C's go with each one of them, but if you work in anisotropy, you deal with that. Yeah.
Hexagonal is 5, and that's usually what people are willing to go to, if pressed. I mean, seismology, it's hard to do more
Oh,
than that.
seismology, maybe. I like 2, but... But in terms of crystals, I don't know. Is there a crystal with 21 independent elastic constants? They actually say.
Yeah,
triclinic
crystals
crystal
are-
as well.
Yeah. Yeah.
What is important here is to define what is the representative volume elements that you consider, because here we're speaking about crystal symmetry, so that would be the scale of a grain. But usually you probe something which is larger, which is a rock or an assemblage, and then it's the texture which will govern the effective symmetry that you will deal with. So.
Yeah. So you'll have a whole lecture on anisotropy, but you're right. And if you remember the wavelength thing that I talked about, typically we're looking at a volume of rock, not even a rock in your hand, but 50 kilometers by 50 kilometers of rock. So you're looking at all the symmetry, the textures in there, even compositional layering within there.
So you're not at the scale of a crystal here.
Well, but even that has a role, right? If it's all olivine, but LPO, if a lot of the olivines are lined up in a certain direction, then the anisotropy of the crystal gives you the anisotropy of
But
the...
they're never
Rock.
aligned, all of them.
No, but if the proportion of them are that way.
I mean,
But
so
anyway.
those summas, those sigmas, I mean, there's, we could probably do a whole cider just on how to sum things properly.
Oh yeah, if you have a whole bunch of different minerals, what is the average
If you sum over
C's for that
constant
rock
stress or
is
constant
no
strain,
exact sum.
Not
all of that
trivial,
goes
yeah.
into those summations.
So, like I mentioned, I only like 2 constants. So, and a lot of seismology is, I mean, maybe I'm going to run out of time, but maybe one of the usefulnesses of this is a lot of seismology that we do involves approximations. One of the approximations we do a lot of is assume that materials are isotropic, even when we know they're not anisotropic, but we can still get some information out there. You keep in mind always there's some approximations involved. So, and that's not to speak that people are not looking at anisotropy, directional dependence. There's a lot of work being done on that, but the vast majority of especially lower mantle studies assume what's called isotropic. And isotropic means there is no directional dependence of the elastic properties of the material. In other words, you squish it this way, that way, you are going to get the same deformation for any direction. Okay, so that's what isotropic means. And in that case, you only need 2 elastic constants. And I think intuitively it makes sense, because you can imagine 2 atoms, there's some resistance to being pushed closer together or pulled apart. And there's some resistance to atoms sliding by each other. And any relative movement between 2 atoms is a combination of those 2 things. So I think intuitively it makes sense that if you have isotropic material, you have 2 elastic constants. And it turns out the equation relating stress to strain in the isotropic case, it's the same equation as this, except we're using different letters, is given by this expression. So the lambda here and the mu over here are the 2 elastic constants that we, by convention, use to describe isotropic stress-strain relation. Linear elastic again. I didn't write down, I should have, probably most of you know this delta ij, it's the Kronecker delta, so if I is equal to j, it's equal to 1. If I is not equal to j, it's equal to 0. So let's say sigma 1, 2 here, this would be 0, delta 1, 2. It's just 2 mu E1, 2 in that particular case. The elastic constants are called Lamé parameters. The mu has its own name, the shear modulus or the rigidity. Lambda doesn't have a name because it's kind of difficult to actually measure directly in the laboratory. So 2 elastic constants, important equation here.
Question.
Yes.
Yeah, I have a question. So if we have 2 different minerals with different structures, how do we deal with the sea?
Excuse me?
So if we have 2 minerals with different structure,
A rock with different,
for
Minerals.
example, one cubic and one octahedral structures,
wow.
how do we deal with the sea?
I think in seismology you don't deal with it.
The mantle is olivine.
I mean, as Abby said, right, there's 2 end members, the Vogt and the Royce average. One is constant strain, one is constant stress, and I think you can make an argument the Vogt average is not a bad thing for seismology, and that's just the arithmetic average of the properties.
So you can average 1 over the values or the values themselves. But I was not
Right, but I
really
think
joking.
in
If you take different anisotropies in the rock, I'm not sure any seismologist really worries about that. Now, I might be wrong. We're going to have talks on anisotropy.
Depends on
But-
what scale.
Yeah, you have
Yeah.
lots of crystals to average over for one seismic wave.
Becomes a
Right.
rock.
Yeah,
so in that case,
but
in
you
the
can have
simplified
boundaries
case-
between domains that you can resolve.
You mean a layer of one type and a layer of a different type? Is that what you mean?
Not necessarily a layer. For example, the boundaries of the LLSVPs. If you have anisotropy outside and another type of anisotropy inside, you can actually
Sure.
resolve it on some wavelength.
And we can try to do that. But the averaging of all the, upper mantle, you mentioned pyroxenes and olivines and maybe garnets, and they all have different anisotropies. And I'm not sure as seismologists we worry too much about trying to get really what the elastic constants in that case are for a hunk of rock. So I could be wrong, but
Again, it's a scale issue. What
it's a scale. You got all those crystals and grain boundaries on top of that, so fabric, etc. So generally what we do in seismology is assume some simple symmetries. An axis of symmetry, vertical axis of symmetry, we assume everything the same in that plane, different in the vertical. That gives you 5 elastic constants. In seismology, we might do that, but we're not actually worrying about the individual minerals like you might worry about that gave us that. That might happen from fabric or some layering and structure, and there's a reason to look at that. But, anyway, I'm sorry, somebody else had a...
So basically, the seismic wave is traveling at kilometer per second velocity, and you're only worried about the waves with frequency less than 100 hertz. So that means you're averaging over the scales that is larger than at least 100 meters.
Oh, absolutely, yeah.
So you're thinking of averaging 100-meter things. So that's
It's worse than that. You're in
Yeah.
global
Or
seismology,
kilometers.
you're averaging tens of kilometers.
right.
And anisotropy, it comes from a very small scale then.
Yeah. So I guess one of the things, connecting small scale to seismology is really an issue. Yeah, you're right. Yes?
Now, wouldn't like exploration seismology, wouldn't they worry about like you go through a clay, how these clay particles are oriented?
Yeah. So in exploration, they are really dealing with anisotropy, especially in shales because of the clays, and they're highly anisotropic. But still, they're looking at 10-meter type wavelengths. They're averaging over 10 meters. But the clay minerals tend to line up, and it's huge anisotropy, so they worry about that. But they treat it in a really simple way, this transverse, vertical axis of symmetry, and then symmetric. So they're still using simplifications, I think. Okay. Anyway, we're down to 2 elastic constants, lambda and mu. I want to mention there are other elastic constants. So I mentioned this already. If I is not equal to j, sigma ij is equal to 2 mu eij. So it's just the resistance to shearing. You put a shear stress, you get some shear strain, and mu is the resistance to that, or the shear modulus. Bulk modulus, I think this has been mentioned a few people, and I think in seismology it's the adiabatic one, constant entropy. But anyway, it's the measure of the incompressibility of a material. So you put normal stresses and pressure on all sides of a block. What is the fractional change in volume? The bulk modulus gives you that. It's the resistance to compression, so the incompressibility. But you can relate it to those other 2 elastic constants, the lambdas and mu's that we previously introduced. So lambda plus 2/3 mu. And the last one I put up, there's others as well, is Poisson ratio. And I mention this because a lot of papers in seismology, they say, oh, we found the Poisson ratio of this hunk of rock is equal to 0.4, therefore it's partially molten. So what is Poisson ratio? Basically, it's related to an experiment. You take a cylinder of material and you're pulling on the ends of that cylinder. On the sides, there's no stress, no constraint, so it'll get longer, but it's going to get thinner. And the Poisson ratio is the ratio of how much thinner it gets to how long it gets. And you can show that that's actually related to those lambdas and mu's as well. It's lambda divided by 2 times lambda plus mu. I should mention that in seismology anyway, we call a fluid, a liquid, is something that has zero rigidity. So if you have viscous fluid, like Michael talked about, that's not true anymore, but in terms of linear elasticity, 0 mu means you have a fluid, atoms can slide by each other freely. So in a fluid, the Poisson ratio, mu is equal to 0. It's just lambda over 2, lambda, it's 0.5. Going in the opposite direction, that's as big as it can get. If mu goes to infinity, not very physical, this can go to 0. Usually in most rocks, lambda and mu, solid rocks, are about equal. So the Poisson ratio is about 0.25 for rocks, usually a little bit less, but not too far. But it goes up to 0.5. So a lot of times seismology papers, you're trying to measure Poisson ratio. I'll show you how you can do that. And if it's a high number, above 0.3 or so, you really have a weak rigidity, which might be due to partial melting or some fluids in your rock. So, go beyond that.
Are there any scaling relationships between, say you have a partial melt region, so solid liquid, rigidity of that mixture, various bounds and stuff that people come up with?
Yeah, and they do that a lot in exploration, I know. I'm not so sure in our field, but so they have equivalent media properties. People have done the work with kind of ellipsoidal shaped fluid things, pennies, in the fabric. And there's equations to get, the overall, the bulk elastic properties. You were asking basically the same question before about anisotropy, but here you're just even worried about the bulk modulus or some things like that. So those equations exist. I certainly didn't write them down here, and I don't have them memorized personally. But I know where they are, but they do exist. So I'm going too slow. Let's get to the seismic waves themselves. Basically, seismology is pretty easy. It's F equals ma, Newton's law. Force is equal to mass times acceleration. What do? You're looking in this big hunk of rock, the Earth, a little element of material there. You look at all the forces acting on that little element, and you equate that to mass times the acceleration. And that equation is written down here. This is the index notation, so there's 2 J's here. That's derivatives. And I'm going to go through this pretty quickly. So the mass times acceleration is over here. Density. These things should all be multiplied by volume, but they all cancel out if we did the derivation in detail. But this is the acceleration term of F equals ma. Density times the second time derivative of that displacement vector that we talked about before. What is over here? Well, acting on this element, there could be a body force, gravity, for example, or something else. And then there's derivatives of the stress matrix. So where does that happen, or where does that come from? So if you're looking at the overall force on this, let's say in that direction, you have one component of force in that arrow in that direction, and this is pointing, if it's a positive number, in the opposite direction. The difference between these two gives you an overall force in the right direction, the 2 direction. Okay? The first order, that's the derivative of sigma 2 as you go in the 2 direction, times the distance apart they are. The overall force is times the area here. So the force due to a particular stress, and I just use 2 as an example, I equal to 2, J equal to 2, it's the derivative of that sigma 2 as you're going in the 2 direction. The force itself, that's force per unit area, you multiply by the area, you get the dx1, dx3, so this is where one of the volume elements comes up. It's obvious in the density, you want mass here, you have to multiply density times volume. Force per unit volume, you multiply by volume. These gradients in stress give you overall forces on an element, and they're also multiplied by volume, so they cancel out. So this is just F equals ma. I think intuitively anyway it makes sense. Gradients and stress give you the overall force plus the body force. Okay? And that's really, let's call it the equation of motion, fundamental equation, and as Michael kept referring, not many approximations in that particular equation. So we will look at the case where we don't have any body force. If you do normal modes, you have to worry about gravity and things like that. But more significantly, how do we put in sources? How do you create these seismic waves in the first place? You have explosion, earthquake or something makes those waves. Mathematically, we treat them by finding an equivalent body force to describe an earthquake. Okay? So if I drop the body force here, I'm basically looking at how do things move around, or how is displacement related to stress gradients far away from the source. And we'll get some interesting things from that, but that's really what we're doing. So we'll look just to solve this equation. You have stress here, you have displacement, so I'm not sure how to solve that. Let's make one variable so we can solve one equation. We already saw the relationship between stress and strain. We had a relationship between strain and displacement. So I didn't go through all that business, but you can get stress and displacement. And this is kind of ugly, but it gets worse, so don't worry about it. Different letters here. Remember, if they are repeated, you're summing 1, 2, 3. So that's actually 3 different terms over here. Delta function. So this is relating stress to displacement. Okay? For linear elastic isotropic material. If you had anisotropic, this equation would still have these u's, but it would have a whole bunch of c's in there, not the lambda and mu, but same idea. So we can plug in, for the stress here, this equation, and then you have an equation which is just in terms of u, displacements. And that's going to be the fundamental equation in seismology. We'll call it the vector wave equation. So let's do that, and you can see, I'm not going to go through all those details, you've got a ton of different derivatives. So you can kind of group terms together, and what you end up with is a god-awful expression down here, which is an expression which is all this displacement vector. This bold means it's a vector. Sorry, so this is actually 3 different equations. One equation for ux, one for uy, one for uz. And I notice I use dots instead of time derivative. If you put a dot on top here, it means it's a time derivative, so that's the mass times acceleration term here. All this other stuff just came from plugging that into that term over there. And why is it so messy? Well, there's a derivative of this. And an important point is, I'm taking a derivative of this. I have these lambdas and mu's here. If they vary with position, so they depend on x, y, z, then I have to take a spatial derivative of the lambdas and the mu's. And that shows up in this term here. You have a gradient of lambda, and here you have a gradient of mu, times complicated stuff here and over here. And these two terms are when you're taking the derivative of what's inside the mu and the lambda. Okay? So it's a really nasty looking equation. And, well, what is it giving us, though, this equation? Remember, u is the displacement. So you can imagine, let's say there was an earthquake or something, some explosion. It causes some displacements. That'll be our boundary condition, our starting point. You know displacements of all these atoms at some given amount of time. Calculate all these gradients over here, and it gives you the acceleration of those different points. So you can kind of step through spatial, you get the displacement, you get the acceleration, how they change, go back, etc. Solving for mu is basically solving for movements of the ground from a starting point, some kind of disturbance starting point. To get that starting point, we have to put in that body force that I talked about. Really nasty. There's no nice analytical way of solving that. There are 3 approaches used in seismology, general approaches to dealing with that equation, assuming that the real Earth has a lot of random variability in properties, so the lambda and mu depend on space. One approach is to assume that, yeah, the Earth has a lot of different rock types, but we'll assume they're hunks that are homogeneous, layers if you want, of homogeneous rock, and then another layer, different properties, homogeneous, another layer, homogeneous. Within those homogeneous rocks, we can drop those gradients of lambda and mu. That's what makes the equation really hard to solve. So that's simplifying the Earth model, but then it turns out we can solve for the displacement exactly. That's been done a whole lot. Very productive approach, actually. We're lucky in the Earth because to first order, the Earth really does seem to be layered as a function of depth, crust, mantle, core on a big scale, but even on a smaller scale, there seem to be variation in properties with depth, which are stronger than the lateral variations in properties. So that's one approach. Second approach is, instead of approximating the Earth, we'll approximate solutions to that equation. And here we will, usually these things work better the higher the frequency of the wave you're looking at. And if you can neglect the gradient terms, it's pretty much the same thing as assuming homogeneous. If we neglect these terms in the solution, but we'll just have these two terms here, but we'll let the lambda and mu depend on position, but we can kind of solve this approximately anyway. So there you're not approximating the Earth so much, you're approximating the solutions to the equation. And sometimes it works well, and sometimes it doesn't, wrong direction. Okay? And that's basically ray theory and some of the results in ray theory, and we'll talk about some of that later on. And the third approach, which is just becoming really feasible now, is just to brute force try to solve that equation numerically by finite element or finite difference. We still cannot do that on the biggest computers at, say, 1 Hertz frequency. The time to solve the equation depends on frequency. The higher frequency waves to go through the whole Earth is still a gigantic problem to solve, but that's the most accurate way to solve what we'll call the forward problem, to actually compute what the U is, the displacement, for a given source, for a given model of the Earth. What is the displacement over there from that? You can do that numerically, but it takes a lot of computer power. So those are kind of 3 approaches in seismology. Let's take the homogeneous medium approach, which is the easiest. So I can drop the terms in the gradient of lambda and the gradient of mu, and you're left with this equation over here. And that's after some manipulation of the equation. Again, it's just vector calculus and using different relations. But rho u dot, the double time derivative of the displacement, is equal to these 2 terms here. You can take the divergence of that equation, and the divergence of the curl is always equal to 0. So you end up with this equation over here. If you take the divergence where the alpha here is just the lambda plus 2 mu over rho, which show up over here, and basically you have something called the Laplacian, double x derivative, y derivative, z derivative of the divergence of the displacement field minus 1 over alpha squared, double time derivative of the same thing, the divergence of the displacement field equal to 0. If you take the curl of that equation and then use some vector relations, kind of just some arithmetic detail, you get an equation like this, which is exactly the same as that equation, except instead of your variable being the divergence of u, it's actually the curl of u here. So it's the Laplacian of the curl of u minus 1 over beta squared times the double time derivative of the curl of u. So these equations are identical, it's just they're 4 different things, but they're both related to the displacement of the material, some property of the displacement. The beta here, beta squared, is just mu over rho. These are probably familiar to everybody where they came from, but they come from a lot of manipulation of this particular equation. Nothing really profound in there, though. So these equations, I'm not going to do like Michael and ask you what it is, because I saw the response yesterday. So they're the wave equation. Okay, very famous equation. We know the solutions to these equations. They've been looked at for a long, long time. And
Steve, you said there's nothing profound, but the material properties that enter are kind of profound in a way. Back a slide, right?
Yeah.
The first one has both elastic moduli. The second one
only
one.
So I will talk about, the alpha and the beta. What is not profound is the arithmetic to go from here to there. It's just It's just a lot of arithmetic. We're using vector calculus relations. The equations are very, very profound. Beautiful, in fact. But, so. Anyway, wave equation. And I kind of apologize for this slide. There's just a lot of information there, and I didn't want to actually go through it. So what is, like I mentioned, we know the solution to the wave equation. And a general solution to the wave equation, recall those two equations are the same equations, but one is for curl of u, one for div of u. The general solution is any function f of n dot x minus ct, where the c here could be the alpha or the beta, depending which equation you're looking at. N here is just a unit vector. So you can put any unit vector in there, dot it with your position x, y, z, minus alpha t for the first equation or beta t for the second equation, and that satisfies the wave equation. Okay? What is f? It could be any function. So it could be a cosine or a sine if you want. But more realistically, the f, I would say, would be that pulse shape that I showed you from Bolivia. Right? It went up, down. That pulse shape could be the function f. And you satisfy the wave equation if the variable is given by that. So what does this represent? N dot x minus ct. It actually represents a plane in space perpendicular to the vector n hat. So if you give me an n hat, then that's describing a plane perpendicular to that vector. And if the solution is of this form, it represents a disturbance on that plane, whatever it is, whatever f has at, say, time equal to 0. You will have that same disturbance a distance c away, 1 unit of time away, okay, on a plane again. So it represents plane waves. So you can think of these planes here as being snapshots of the wave, the pulse, at different times. And the fact that the solution has a form like this, that's all the wave equation tells you. That whatever you have on one plane, you're going to have on a similar plane, but a distance c away, 1 unit of time, 2c away, 2 units of time. So it's propagating. The beauty, the profundity, if you want, of this solution is f can be any function. It could be a really big function, large amplitude. It could be just a little blip, okay, a tiny little disturbance. It could be a very long wavelength, a smooth disturbance, or it could be a sharp pulse. According to our theory, the disturbance will travel at the same velocity. Okay? The velocity that it travels at, that's the c here, that's the alpha or the beta. And that only depends on the material properties, and it's the only reason seismology is good is because those speeds depend on the material properties of the medium. So you can solve the same wave equation. You can put it in spherical coordinates. Maybe that makes a lot more sense. If I had a bomb at a point, I expect a spherical wave, not a plane wave. And you can put those Laplacian and spherical coordinates, assume some symmetry, and you find you get a similar solution. It's again any function of all r minus ct, where r is the radial distance from the center point of the c. What is different here is that the amplitude decays as 1 over r. This solution, that plane wave, it goes at the same amplitude forever. Okay? So that was divergence of u and curl of u. What is actually happening? It turns out that divergence of u equation, which is traveling at a velocity lambda plus 2 mu over rho, square root of that, represents particles that are moving perpendicular to the plane. So they're in the direction that the wave is moving. They're in the direction n, if you want. The other equation that we had, velocity mu over rho, for the curl of u, represents a wave where the particles are moving in the plane. The plane is moving perpendicular to itself, basically, at the velocity square root of mu over rho. We call this kind of wave the p wave, that kind of wave the s wave. The nice thing here is if you are in homogeneous elastic material and you don't have a body force, you don't have your hands in there deforming things, that's the only kind of disturbance you can have. You have p waves and s waves. There's nothing else that can exist there. So you're kind of guaranteed that. So I don't know. This is worth it. This is so nice. This is Lev again had these videos of what happens in a p wave. So the wave obviously is going this way. The particles are just moving back and forth. You see deformation of the black thing here, and let's do the S wave over here. And here the particle movement is perpendicular to the direction that the wave is moving. So this is an example of an S wave. That pulse that just went down here traveled at the speed square root of mu, the rigidity of this material, divided by its density. This guy traveled at the speed square root of lambda plus 2 mu. Same rock, the S is always slower than the P because lambda is always a positive number, at least as far as I know. So, let me introduce some nomenclature because it actually is kind of important to read papers in seismology, and it's even been mentioned before. If I have a P or S wave coming up in this direction, so we're talking about that plane wave, so you can think of a plane here traveling up, motion in the plane. If it's a P wave, you are guaranteed the motion of the atom, the particle motion that we talked about before, is in the direction that the wave is traveling. If it's an S wave, I have this plane, and I should have brought a cardboard or something. You can imagine any kind of motion within that plane. It's still an S wave, it satisfies the equation, it's fine. We have a convention to break the S-type motion into two parts. One part we call SH, SV. So it's like two coordinates if you want, for any kind of function if you want. The SH has motion totally in the horizontal direction. So that would be coming in and out of the blackboard here. The SV component of S motion has a vertical component as well as a horizontal component. Now notice the SV horizontal component is in the same direction that the wave is traveling. Sometimes we call that the radial direction. The SH component here is perpendicular to the direction that the wave is traveling. And we call that the tangential direction for waves in practice. So we divide S waves, kind of artificially, into these two type components. There's a good reason for that, because we will see that SH in an Earth that has flat layers behaves very different than the SV. Our wave equation, and S is an S, it could have particle motion in any direction. So that's kind of just a convention of nomenclature, but it's kind of important. So to review a little bit, we have these P waves and S waves. They depend solely on the elastic constants and density of the rock. Different way for shear waves. It depends on the rigidity and the density. P waves, lambda and mu, as Michael mentioned, and the density. We mentioned other elastic constants as well. Remember we talked about the bulk modulus is equal to lambda plus 4/3 mu. So you can write these speeds in terms of other elastic constants. And a common one is to write that as kappa plus 4/3 mu. This is the bulk modulus and the shear modulus divided by rho for the P wave speed. And I'll mention one thing that I think comes up for mineral physicists. Notice that if we write P wave speed this way and S wave speed that way, if we can measure the speeds of those rocks in the subsurface, then if we take the P wave speed squared minus 4/3 the shear wave speed squared, we get kappa over rho. Okay? And we even have a name for that. We call it the bulk sound speed.
That should be bulk sound speed squared.
Yeah, absolutely.
Yeah.
Yeah, actually. Yeah, good. So anyway, maybe we'll hear about that at CIDR, bulk sound speed. We can't measure that directly, but you can get it from the P and S waves. So I thought I'd just mention a few things. These are empirical, or maybe the mineral physicists can explain it all. But empirically, from a seismology point of view, temperature goes up. We find empirically these P and S wave speeds go down. The temperature goes up, the density should go down, so the speed should go up. So it's telling you the elastic constants, kappas, the mu's, and the lambdas must be going down quicker than the density when you increase temperature. And pressure, it's the opposite. So pressure goes up, we notice the velocities go up, those elastic constants are getting stronger, faster than the density is going up. Chemistry, well, there the density part in the speeds is important. So if you take olivine, we've seen that before, FeMg2, SiO4, Mg and Fe can go in there. If you put more iron into the olivine, its velocity will drop, as its density goes up. Iron has a higher molecular weight. And it doesn't affect the elastic constant so much. And there I'm not an expert, the mineral physicist can say, but basically you're just increasing the density. Velocity drops. In general, though, if you are at a constant chemistry, what you find is that if the density goes up for whatever reason, you increase pressure or whatever, the velocity goes up. And that's Birch's law. Birch noticed this way back in the 50s. So a lot of students, anyway, my experience is they always think, oh, density goes up, velocity goes up, but that's only true for a constant chemical composition, a constant molecular weight. So phase transitions, always if the density goes up, the velocities go up.
Wait a minute, is it that the velocity only goes up because I think as you said before, because the elastic properties increase? It becomes
Faster
stiffer
than the
more
density.
rapidly than it becomes dense.
Exactly.
In fact, if you held stiffness constant, I mean, the velocities...
Then they would go down if you could do that.
It's inversely proportional to...
Absolutely. So the rho is at the bottom. Right. Sorry, I mean, that's kind of assumed all through here. So this is a case where you're keeping the elastic constants pretty much constant. The velocity drops. This is just saying for almost all the phase transitions, and again, I'll get in trouble here, but if you have a phase transition, you go to a denser phase, the velocities tend to go up. Always the elastic constants tend to become stiffer quicker than... And I don't know if there's an example that breaks that rule, but
Stishovite.
Stishovite is bad. Okay.
Just in terms of near the phase transitions, some minerals do undergo softening.
That's the softening in the transition, though, right? But the
Silica glass is another example.
Okay.
Silica glass softens as you squeeze on it.
Silica has, and magnesium silicate. Some of them have soft mode phase transitions.
But that's in the phase transition zone, if I understand correctly, right? Where there's a mixture of phases?
No, well, in preceding, if one thinks about it from low pressure perspective, one increases pressure, there is a finite range of pressure. Sometimes it could be 10 to 20 gigapascals, depends on the temperature, that there is softening of elastic constants, which then lead to a softening of the isotropic properties, K and mu. Not necessarily related to the mixture, but just the mechanism of the phase transition. So
Right.
it could be over several tens of kilometers in the earth.
But eventually the stishovite is a very fast mineral, right? I mean,
Right,
yeah.
right.
Anyway, I noticed I'm running out of time. So volatile content, unfortunately, can change the velocity, even a little bit of hydrogen ions, partial melting as well. So I'll quicker, oops.
Are there any heuristics about, let's say, slowness of velocity of both P and S are due to fraction of melt? Can you look at the difference in the slowness of the S relative to the P and extract something about melt fraction
Right.
in any kind of robust way, or is that just...
Well, it really depends on the wetting angle and the mineral grains. So how is the melt distributed on the mineral grains?
Let's say it's a really good wet grain balance.
Then you're going to kill the S velocity very, very quickly, even with a small percentage of melt. If it's in a tube, though, so you don't have much of a wetting angle, then the effect is less. So I think, and again, I'm not an expert in that, but people really worry about that kind of calculation. And kind of a lot of people assume, you look at the PS ratio or you look at the Poisson ratio, and you find zones like the low velocity zone of the Earth where the S is killed a lot more than the P, probably partial melt. But to get a percentage of partial melt really depends on the details of the wetting angle that, maybe that's petrology, I don't know, but yeah.
So I'll talk about that a little bit on Thursday. Right? So.
Okay, what did so actually going back, I'm sorry. All you can do in seismology, we often say, seismologists, I discovered a plume or I discovered a partial melt. Or really what we discover are, if you're a real good seismologist, density and elastic constants. If you're a so-so seismologist like me, you discover just the velocity, some combination of the elastic constants and density. And that's really all you can get out of seismology. So the interpretation depends on a lot of other factors, and that's you're kind of stuck with. But I think that's an important point to remember. Now, I did lie to you in a sense. I said linear elastic, we do that in seismology. rocks are not totally quite linear elastic. So as you deform the rock, there is a little bit of, for a better way of describing it, a little bit of friction going on. So the energy is absorbed, you heat up the rock, and we call that internal friction or maybe intrinsic attenuation, and the effect of that is to decrease the amplitude of the wave, and that is not linear elastic behavior. That's some kind of other behavior. And a lot of times, well, we kind of take that into account after the fact. We have our basic elastic equations. We take that into account after. I mention it here because it's actually kind of important for seismology. We define this absorption or this internal friction, how it's related to energy, by this number capital Q. And capital Q is defined, or 1 over Q, as the fractional loss of an energy in one oscillation of deformation. So kind of implicit in the deformation of Q is an oscillating deformation. One oscillation of deformation, one period, fractional loss of energy with a 2 pi in there gives you the Q. High Qs means very little energy loss. Low Qs, you're absorbing a lot of energy. With this definition of Q, you have a pulse of energy, one of those plane waves, traveling along. Its amplitude will decay by this exponential factor. So this is related to oscillating deformations. Turns out the Q is pretty much the same for different frequencies in the seismic wave. So let's assume Q constant for the time being, doesn't depend on frequency. C here is the velocity of the wave, alpha for P wave, beta for S wave. The omega here is the frequency of the wave. So what you see here is, wow, this exponential decay in amplitude depends on the frequency here. Okay? So the high frequency waves for a given value of Q really get knocked down relative to the longer period waves. You also have the velocity in the denominator here. S waves go slower than P waves, so they get knocked down because of the velocity as well. Okay? Exponential decay with frequency. Even worse for the S waves is most of the mechanisms for this internal friction involve shearing type deformations. And in that case, the Q for the P wave is 9/4 the Q for the S wave. Remember, larger Q, less attenuation, so the P waves are less attenuated than the S waves. And therefore, for S waves, in fact, you rarely see an S wave at 1 hertz. For P waves, they're beautiful. You can see them all you want. S waves really get knocked down in attenuation. We tend to use longer periods when we're looking at S waves. So those are the kind of the two implications here for the effect of Q just on the wave amplitude.
Steve, this
Yes.
is angular frequency, right?
Yes, 2 pi f, right? Yeah. But it's still proportional to frequency. Only have 4 slides. There are a lot of mechanisms for this absorption, and they all have to do, or most of them have to do with defects in the crystals. So it's bad enough that we have different crystals that you guys slammed me on before. But even within the crystal, there's deep point defects, there's dislocations, grain boundaries. That's where the absorption is taking place. There's a lot of different mechanisms. Most of these are temperature related, temperature activated. So a lot of them have to do with breaking a bond within the crystal and then a new bond forming. The higher the temperature, the easier it is to break the bond. So the Q for those kinds of mechanisms is related exponentially to 1 over the temperature. Very, very sensitive to temperature. So if we can measure Q, that gives us something beyond just elastic constants and density. We might actually have a direct way of getting at temperature. These other constants in here, this is an activation energy. Maybe Woolley knows a lot about that. We don't know that so well in the Earth, but, and it's also harder to measure Q, but there's somewhere to go in seismology to get at temperature. So that's one comment there.
The alpha is different from the alpha you used in the previous slide, right? Because in the previous slide you...
Oh, P velocity? I'm sorry. Yes, it's totally different.
Yeah, just to make sure.
Yeah. Apologies there. And actually, and it's not just me. We use alpha for P wave speed, and we use alpha for the frequency dependence of Q in seismology literature. So, the Greek letters.
Maps of the Earth with Q?
Yes, Barbara actually has done some of the seminal work on that. I don't know if you'll agree with me. I think we have a long way to go before those maps are as high quality as the velocity tomography maps. But I do think it's a direction of research which is actually kind of exciting because it really gives you some, all we have elastic constants and density gives you some more information. And I bet it's related to melt too. I bet if you looked at the partial melting zone, it probably has an effect on Q. So this kind of Q is kind of uncertain. These are 1D Q models, much less 3D maps. And so there's a whole bunch of different ones. I don't have a favorite or anything. My point is it's all over the place. This is just the average Q for the Earth as a function of depth.
Looks like viscosity.
Yeah, and they're related. The mechanisms are related. I guess the one thing...
Sigma.
Yeah.
Some Greek letter.
Well, not quite orders of magnitude, though. Right, we're just maybe one order of magnitude. But I think what everybody agrees on is you have much lower Qs, which means higher absorption in the shallow part of the Earth, and higher Qs down in the lower mantle. And there's kind of viscosity in the lower mantle, critical, and yeah, the Q is all over the place. But it's all pretty high. So not too much absorption, but a lot of absorption in the upper mantle. And the last thing interesting or important about Q is if you look at the theory, if you have this friction in the rock, you must have a frequency dependence of those elastic velocities. They must depend on frequency. The linear elastic theory, and we got a velocity, and we didn't talk about frequency. All frequency is the same. If you have absorption, the velocity of the seismic wave depends on frequency. And sometimes people confuse, even I was talking to a friend, he said, oh yeah, frequency dependence of Q, that'll give me dispersion. No, even if the Q is the same at all different frequencies, you still have a velocity dispersion. So often inside the simplest model we have, and this is a figure from Peter Shearer, is this is 1 over Q. So you have this band here, this is frequency down here, and the Q is constant within that band. This is usually the seismic band, so I don't know what happens outside the seismic band. But within that constant frequency band, the seismic velocity, C here, and this is the angular frequency, depends on the frequency. Seismic velocity depends on the frequency. And if you talk about Qs of 100, like in the low, 200 kilometers deep in the Earth, you're talking a couple of % variation in seismic velocity, just in seismic studies, from a 1 hertz body wave to, say, a long period surface wave. That's a couple of % difference. If you talk about mineral physics at a gigahertz, and you're trying to compare those velocities to seismic velocities, that's many, many orders of magnitude. And I've always worried about that in comparisons. But I can say I think you absolutely have to take that into account some way. We don't know the Q all the way to a gigahertz, but you need some kind of way of dealing with that. And I'm just going to skip that. Maybe Q does depend on frequency. I apologize. Waves in homogeneous media. So we can do exact calculations, solve those wave equations. Let's talk about that quickly in the last minutes. If we have two media, one here and one here, they're homogeneous, no variations. You know you have P and S waves, you know you have P and S waves. What happens in that case? You can solve this exactly. If you have an SH wave coming in, so let's assume this is a horizontal plane. You bounce off, you reflect an SH wave, you transmit an SH wave. If you have a P wave coming in, same kind of boundary here, what happens is you reflect a P wave, but you also reflect an SV wave. You transmit a P wave and you transmit an SV wave. And it's the same thing if this were an SV wave coming in here. You get a P wave created and another SV wave reflected and transmitted. The P and the SV are coupled together. This is true for flat layers. If the boundary was, at tilting or something like that, then the SH would be just as complicated. But because we assume flat layers, and the SH-SV idea is because of this difference, basically. So how much energy gets reflected, how much gets transmitted? For SH, the expression is not too bad. This is the amplitude for an SH wave bouncing off. It depends on the angle coming in as well as the angle going out. Here is J, there's theta. I'm sorry, they're the same thing. It's just I was grabbing the figure from a different equation. So that depends on the angle the waves are coming in, but maybe more important is it depends on this combination of the density times the velocity. We call that the impedance. It's the difference in the impedance between the two materials that govern the reflection of the wave. And if you're a good seismologist and you see a wave bouncing off a layer in the earth, well, you can get the contrast in density times velocity in that case. And if you know the velocity change from some other approach, you can pull apart density and velocity in that case. So kind of complicated expressions. For a P wave coming in, the expressions are really god-awful. They're terrible, very complicated, but they depend on the same thing. PS velocity, density, PS velocity, density, and the angle the wave is coming in. People have heard about receiver functions. We use this idea of converted waves. So a lot of times this is the crust, this is the mantle, but it doesn't have to be. If you have a P wave coming up to a station over here, part of that P wave will convert into an S wave. S wave velocity is slower than the P wave velocity, so this will be a post-cursor to the actual P wave that came up. How can you distinguish these different waves coming in? Well, there you use your knowledge that for the P wave, it's mostly motion in the vertical direction. And for the S wave coming up, it's mostly motion in the horizontal direction. So you try to pull those two things apart. You get little blips for these converted waves. If you know the velocities there, you can calculate the depth of different boundaries. If you've seen receiver functions before, maybe something good to know is that conversion coefficient depends mostly on the shear velocity difference. So when you use receiver functions, you're mostly seeing the jumps in shear velocity. How about the angle that waves travel at? Well, that does not depend on density at all. It depends on the velocity contrast from one media to the other. And what remains constant in that case, maybe most of you know this, it's the same in optics, Snell's law, it's the sine of the angle of incidence, and we always take that from vertical, divided by the velocity. That remains constant as you go from one layer to the next. And really that's required by a continuity of the wavefront as it's coming in. So Snell's law is applicable in seismology. If this was, say, a P wave coming in and an S wave propagating down here, it's the same Snell's law. You use the S velocity here and the P velocity there for the upper media. So Snell's law connects all these things. This quantity describing the direction of the wave, since it's constant, we give it a name and a symbol. It's the ray parameter. So a lot of the equations we use to track rays, you assume the ray parameter is constant. You go through the different media and you can track the rays. You have an interesting... Dang. Let me see, Wiz. Let me go right to ray theory. We'll skip that. So the approximate solution, reflections, refraction is very important. If you use the approach of let's take the media to be varying in all directions, approximately solve the equation of motion, you get ray theory. And what happens there, ray theory basically says the wavefront will propagate out at the local velocity, whatever the lambda and mu and density are at that point. That's the speed that the wave will propagate out at perpendicular. So we call the perpendiculars to the wavefront a ray path. And ray theory says you will get motion at a certain point if a ray arrives at that point. If no array arrives at that point, you get no motion. That's actually a simplification. It's an approximate thing. It allows you to calculate travel time because you just integrate 1 over c, 1 over the velocity along a particular ray path. You get the travel time. You should get a wiggle there. And we use that So if we have increasing velocity like this, so smoothly varying, we're using the ray theory, what happens is the ray paths will obey Snell's law still. They will go down to a turning depth, and then they will turn around and come back up. So you get a blip motion here when that array arrives, etc., etc. That's kind of approximate, and I go through where the approximations break down. I just want to mention in the Earth, we can use ray theory because it's really a simplification. Wow, let me jump. This is kind of data we have from ISC. 1 minute, huh? Basically, these are millions and millions of travel time. So every time there's an earthquake, this organization, ISC, they measure the travel times of whatever. They don't measure the travel time. Somebody at a seismic station measures it, sends that information to the people. People at ISC locate the earthquakes, so they know the distance away the station is. And this is just all those travel times plotted as a function of distance, 180 degrees around the Earth. The time here is in minutes. And what you see is these are basically the P waves arriving. They kind of disappear here. These are P waves up here. And this is very classical for a low velocity zone, which I was going to show you, but I don't have time. This indicates basically that the velocity drops drastically at some place deep in the Earth. That's the core versus the mantle. S waves, you can see them here. Arrivals like this, you don't see any for S waves. And that was the indication that the outer core was liquid in the early days. So we can use the time versus distance there to get a model of velocity as a function of depth. And I was going to go through some of the complications, but we do have these reference models based on largely travel time versus distance, not just the ISC, but there's other data sets available as well. It's just time versus distance along ray paths, as well as normal modes and surface waves that you'll hear about later on. We have a number of different reference models, AK-135, IASP, and Dan Frost was telling me he's going to do a little web page thing saying which models are good for which situations. These are average 1D models, and I think Barbara already mentioned maybe we need an average 3D model for the Earth. This is PREM, Preliminary Reference Earth Model. We're still working on the Reference Earth Model. I think most of you know the basic structures here, but shear velocity, P velocity in the mantle. I mentioned that the times show you that, wow, large drop in velocity when you reach what we call the core. And the S velocity apparently goes to 0 because we don't see waves that go through it. Call that the outer core. There's some details in the travel time. We do the inner core, which we think is solid. Upper mantle discontinuities, we've talked about them already. This is a reference model. I think it's worth a whole discussion over how valuable these reference models are actually in terms of some of the fine detail to talk about what is anomalous and what is not anomalous. So that exists out there, and I'll leave you with this video because you're hungry, and I really apologize, but this is kind of neat.
Hungry for more seismology.
What's that?
Hungry for more seismology.
Yeah, okay. I don't know if this is going to work, but
cover over it.
Oh, maybe this one doesn't work for some reason, so you lucked out.
Move your mouse over the picture.
Move
the mouse over the picture and then
there it goes. So this is something Mike Thorne. It really shows you the waves through a PREM-like model. The blue is S and the orange is P. And this is done by finite differencing that wave equation. And I wanted to make 2 points on this figure. One is kind of neat, but one point is these body waves sample all over the outer core, the mantle, etc. I had some examples of different studies where we look at different parts of the Earth. So that's a good thing. The bad thing is this is kind of awful looking, right? So we often, to communicate with people, we use ray theory. We draw a diagram of a ray and you say, oh, okay, that's the S wave coming in and there's a wave reflecting off the core. And I was going to go through the nomenclature of that, but you're kind of required to do that. No seismologist deals with this picture and tries to unravel it, so don't feel bad if it looks complicated. But the picture's kind of neat anyway. So I apologize for not getting through even half, I think, what I think.
Okay, so we might be able to take one or two burning questions. But I would point out there's a lot of seismologists around here that can go into details that we haven't been
I'd be
into.
glad to one-on-one.
Just ask a seismologist if you don't know something about what you just heard or you want to clarify. Are there any questions before lunch? Make yourself very unpopular. Ask a question. I would say one thing in response to the lengthy discussion we had about the CIJKLs. Fundamentally, the elasticity is still going to be F equals ma. It's going to be spatial gradients of stresses in the system balancing acceleration. Two time derivatives on one side, two time derivatives on the, or two space derivatives on the other. You always generate the wave equation. And adding in the other terms for more complicated symmetries than this mythical isotropy, doesn't fundamentally change the nature of the wave equation that arises. So even a complete numerical solution with 21 elastic constants, you get two wave fields, a P wave field and an S wave field. Some of the transport of energy, the details of it does change and is affected by the additional complexity, but not the fundamental essence, that you'll still have a P wave and an S wave. So that'd be my party shot. So everything that seemed like, is it too simplified? It's not. It's capturing the first order characteristics. And there are some details that you get into when you study anisotropy, as we'll hear about later. It's not going to profoundly change the equation of motion.
So maybe the seismologists will want to wave their hands in the air so you can find something about it at lunchtime if you're really bad.
All seismologists stand up.
Oh no. You go to mantle.
Maybe this is premature putting it up there, but I did. So the surface wave, if you think about it, it's stuck on the surface. So as it expands out, the circumference of the circle is increasing as r, distance from the source. The body wave, however, is propagating in 3 dimensions, and the area of the sphere is proportional to r squared. So to conserve energy, and it turns out the amplitude of the shaking squared is proportional to energy, the surface wave's decay is 1 over the square root of the distance they travel. The body wave's decay is 1 over the distance that they travel. And that's why in a lot of seismic recordings, the surface waves are quite large. So let's go on from there. I thought I'd show you an example of a fairly simple seismogram. This is the movement of the ground in the east-west direction at a station recorded in La Paz, Bolivia. And this movement was recorded a short time after a deep earthquake just south of La Paz in South America occurred. So if you look at the recording, very simple, right? It's just how the ground moves in the east-west direction. You see a number of these pulses, boom, 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 coming in time. We call those things phases. They're basically waves, these elastic vibrations that are arriving at the station in La Paz. If you look at a blow-up, let's say just this big pulse here, and I just flew up 100 seconds, or actually my student did, of that pulse, you see that, oh, the ground was pretty stable. The ground started to move west, moved east a little bit, moved back west again, came back to its equilibrium point, and was flat afterwards with a little bit of jiggling. We call this thing the wave shape, or the pulse shape, or the wave form of the particular wave. So I'll kind of refer to that a couple of times later on in the talk. But that's basically what this pulse looks like when you blow it up. So what are all these different pulses? And it turns out in this case it's kind of neat. La Paz was very close to where that earthquake occurred. And what you're seeing with those pulses are waves that went down to the core and up to the surface, also to the surface, and et cetera. So the very first pulse went from that earthquake source directly to the station. The second pulse you saw went down to the core, bounced off, recorded at the station. The third pulse up to the surface, down to the core, back up, etc., etc. And that's what those different pulses are. A lot of seismology is basically about speeds, and you've already heard in a lot of talks wave speeds here and there, ultra low velocity zone, etc. This is a nice little experiment you could do if just looking at that recording. If you know how deep the core is, 2,891 kilometers, you could just look at the pulse. As Barbara said, this is the first talk in seismology. My name's Steve Grant. I'm from the University of Texas. I won't go through all of this, but there's a lot of other topics coming on. I'm going to give you the introductory equations, kind of the real basics of seismology. Some of the later talks will get into the exciting things like tomography and whatnot, but I won't touch on that. So my outline here is a brief introduction, simple introduction to what are seismic waves, what is seismology. Then we'll talk about the fundamental equations, so kind of like Mike was doing with geodynamics or convection. After that, I want to talk about the behavior of seismic waves in different situations. So we'll talk about waves in layered media. We'll talk about ray theory and the basic structure of the Earth. And if there's time, I brought some examples of different what's called body wave studies that I thought were kind of interesting and relevant to the group. So what are seismic waves? Well, they're vibrations or deformations inside the solid Earth that propagate, that travel through the Earth. And everybody's familiar with water waves, so just put a picture up here. You throw a pebble there, you get a water wave expanding out. You all realize this crest in the water propagates out. If you look at an individual molecule of water, though, there, the individual molecules are just going in little circles like that. They don't actually travel with the wave. So I show this because you're all familiar with water waves, but there's two different velocities involved. One is the velocity of that crest. We call that the wave velocity. The other velocity in seismology, we call it the particle velocity, but it's the velocity of one particular piece of material. Notice for the water waves, little atoms or molecules of water are going around like this. As you go deeper and deeper in the water, the molecules move less and less amount. And in seismology, like I said, we have similar kinds of waves, but they're within the solid Earth. And we have two words, body waves and surface waves. So my talk is supposed to be on body waves as opposed to surface waves. Jean-Paul Montier will talk to you about surface waves. The water waves are a good example of surface waves. So the water wave or surface waves in an elastic Earth shake the surface. They also shake deeper down, but they get smaller and smaller shaking, basically an exponential decrease. We call those things surface waves. Body waves, on the other hand, expand in 3 dimensions. So if everything's kind of homogeneous and you had, say, an explosion at a point here, you will get a disturbance in a sphere around that point, and it will propagate outwards in all 3 directions. And we call these kinds of waves body waves. So that's kind of what we're going to be focusing on here. Really, the two things obey the same equations and could be done seamlessly going between the two, but we'll focus on those body waves. I do mention something about the decay and amplitude. So often we take seismic data like the seismogram I showed you, and people will filter it. They will make that seismogram out of a bunch of cosines with different frequencies, different wavelengths. They'll only keep a few of the frequencies and wavelengths in a particular analysis that they're doing. And why I think that's important is whatever you're trying to get out about the interior of the Earth, whatever resolution you're looking at, you are limited to about a wavelength. That's the absolutely best resolution you can get. So whenever you read a paper from seismology, you should look at the period range they're looking at, what are the wavelengths, and you know that's kind of the limit of the resolution. You can get an average property in a wavelength, you just have no idea what the details are within that particular wavelength. So I filtered that original seismogram here, those pulses at La Paz. I didn't mention it before. This was from 1 second to 100 second period, all those cosine waves. And that's pretty much what the ground did. The amplitude at higher frequency than 1 second, very, very small. Longer than 100 second, very small. Pretty much that's what the ground did. If you filter that record 50 to 100 seconds, you get this result. It's a beautiful seismogram, but it looks quite a bit different than that. A lot of the global tomography, we tend to use longer period, not quite as long as that. And here's kind of interesting, this is 1 to 10 seconds, so the shorter periods in that particular seismogram. And there you can see that first pulse here, you can see maybe the second one there. You really don't see these later pulses. The high frequencies have disappeared. You see a lot of other stuff going on. I have no clue what that is, but it's something. So I wanted to make, well, that's the young seismologists will figure all that out. Wanted to make the point about frequency content in seismology because it's very important. We use a huge range of frequencies, over 5 orders of magnitude. The oil companies, reflection seismology, they're looking at 100 hertz waves. Body waves in the deep earth, usually from about 1 second period, maybe 20, 30 second period. Surface waves from about 10, maybe 5 second period, up to a few 100 second period. Normal modes, Miyake will talk about them, up to 1,000 second period. So there's a huge range of these different periods, different resolving capabilities, different usefulness in these different waves.
Could you explain a little bit more, how do you do the filtering exactly? Do you have to Fourier transform it first into the frequency space and then filter there and then transform it backwards?
Yeah. So that's exactly it. You can take a time series. You can do a Fourier transform, get the Fourier components. Usually don't cut off at a particular frequency. You kind of put a window on it and smoothly get rid of them. And then go back to the time domain. And that's basically what was done there. Yeah, just interrupt if you have any question. So that's kind of my intro on the seismic waves. So we'll go through some basic equations governing the waves. They're the same equations for surface waves, normal modes, and body waves. So we'll just do it once, I think, here. I'm not going to show you a whole lot of equations. I think you can look them up. But maybe the usefulness of this is just to see where certain things come from, what approximations were used here, what approximations there, etc. So let's start with that. And seismology is about movements or deformations that propagate. So how do we quantify movement? And we introduce what's called the displacement vector. And a lot of things, I'm going to be repeating what Michael talked about yesterday, but he was using velocities. And I'm glad you didn't use U, you used V. So we're using
mechanics people use U for velocity.
Yeah. So we're going to repeat a lot of things, but they're different. And I'll try to make that clear. Anyway, we introduced a vector. It's a vector field. Every point in space, so let's say x naught is really x, y, z in space, the vector at that point is just the displacement of that particle who at equilibrium is at x0, how it's been moved from its equilibrium position. So the coordinates kind of refer to particular particles. The vector associated with that coordinate is how that particle has moved. So it's a vector, it has three components, right? Up, down, north, south, east, west, whatever system you want. Seismic waves are deformations, and you know the displacement vector of all the particles everywhere. Well, maybe you know the deformation. You do in a sense, but it's not directly the displacement. You can imagine if I said the displacement vector everywhere is 1 in the x direction, 0 in the other directions, just means the whole body shifted a distance of 1, right? No deformation has occurred. So deformation has to do with changes in the displacement vector as you go from point to point. And I should just mention quickly, I'm spending a little bit of time on this displacement vector, because most of the equations in seismology are equations for that thing. So it's important to know what it is. So this, again, came from Ved, a nice little illustration of deformation and how it's related to the displacement vector. He shows different situations. That went up here, and the other one that went up, down, up. Measure the time difference between the two of them, and you can get the average speed of the wave going through the mantle. So it turns out to be about 6.2 kilometers per second. Very simple calculation. But really, a lot of seismology is basically in that way, getting the speed of these waves. This is wave speed, not particle speed. So I want to mention something kind of basic, but I think it's really critical in seismology. And I think all of you have had Fourier series. So you can take any function, and let's take this red one. That's just a pulse, a Gaussian type pulse. You can make it, you learned in college, I guess, undergrad, by summing together a lot of different cosines and sines. So in this particular case, because of the symmetry, these are different cosines with different wavelengths. You add them all up together, you get that black line. If we added more and more, you can reproduce any shape function by adding together these cosines. Fourier series, that's kind of well known, I think. But maybe a little bit less well known is you can actually represent a wave, so a pulse, like that pulse shape I showed you at La Paz, that particular shape, propagating through space. We can also represent that by cosines and sines as well. It's cosines and sines of two coordinates now, the x, the distance, and time. So we can add up a whole bunch of these cosine kx minus or plus minus ft's together, and we can make any kind of propagating pulse. This is a nice little video of how a function like that actually represents a wave traveling. And I'm not sure these are going to... Oh, there it goes. This was made by Ved. And basically, an individual particle is just going up and down like this. But and this is distance x over here, and you're just computing these things as time goes on. So I won't show the video again, but you see the peaks traveling along. So that's the wave propagation part. So we can make any kind of seismic wave out of these cosines. There's a lot of terminology here. the time it takes to go up and down like this at one particular point is called the period for the particular wave. That's 1 over the frequency. The frequency's up there in the cosine expression. Wavelength is the distance between two of these peaks here, or 0 to 0. The velocity of the wave, how the peak travels, is just the wavelength times the frequency. There's a whole bunch of different combinations, wavelength divided by the period, etc.